Okay, let's jump right in. Imagine this. You're looking at your office window, sunlight streaming in, but that window, it's also generating electricity for the building.
Right. Or maybe the sunroof on your car isn't just glass anymore. It's actually helping power the vehicle.
Exactly. Sounds like pure science fiction, doesn't it? But today we're actually diving into a document that shows how this is becoming very real.
It is. We're looking at a specific patent application, US 2250267978A1 from First Solar. And it's fascinating because it tackles some, really fundamental challenges in solar tech.
Moving beyond those standard opaque panels we usually see.
Precisely. This document gets into the nitty-gritty of things called transparent conducting layers
Oh.
and how they fit into the overall photovoltaic device. It's pretty ingenious stuff.
So that's our mission today, right? To unpack the how and the why behind this innovation from First Solar. What does it mean for the future? And explaining it all clearly for you listening. Now, First Solar, Inc. They're listed as the applicant and assignee here, based in Tempe, Arizona. They're a pretty big name in the solar world, wouldn't you say?
Oh, absolutely. A major player. They've been leaders, particularly in certain types of thin film solar technology, for years. They have a significant market share, especially in large-scale utility projects.
So this patent application we're looking at, it's not just a one-off idea. It fits into their larger strategy.
Exactly. You can see this application filed August 21st, 2025, but it actually claims priority way back to September 2020. That shows a long-term R&D effort.
Wow, yeah. 5 years of development just reflected there.
Right. It demonstrates their ongoing commitment to innovation. It's not just about churning out the same panels. It's about making them better, smarter, maybe more adaptable. Think integration, not just installation.
Integration. That's the key word. So what were the big hurdles with, standard solar panels that this kind of tech aims to overcome? What problems are they solving?
Well, traditional photovoltaic devices, they convert sunlight to electricity, sure. But they've always had limitations,
Like,
like manufacturing complexity, for one. Getting the cost down is always a battle. Then there's durability. These things have to survive outdoors for decades.
and the big one you mentioned earlier, they're opaque. You can't see through them.
Exactly. You need dedicated space.
Ah.
This patent, it seems to be aiming squarely at efficiency, reliability, and versatility. Making them transparent opens up entirely new possibilities.
So it's about getting more power, maybe, but also making the panels less intrusive or even invisible.
Sort of both.
Yeah.
The document talks about improving light absorption, better collection of the charge carriers, the electrons and holes doing the work, and just overall higher conversion efficiency. But it also highlights the challenge of working with these different complex semiconductor materials and getting them to play nicely together, especially when you want light to pass through parts of the device.
Okay, this is where it gets really fascinating for me. The core idea, transparent conducting layers, TCLs. How does that even work? Transparent and conducting. It feels like those two things shouldn't go together.
It does sound counterintuitive, doesn't it?
Yeah.
But that's the materials science magic.
Got-
Think of it like, well, like a window pane that lets light through, obviously.
Mhm.
But it also has invisible pathways woven into it that let electricity flow.
Invisible pathways.
Yeah, they use specific materials, usually metal oxides like indium tin oxide or ITO is a common one.
Yeah.
These are engineered at the atomic level to be clear to visible light, but still allow electrons to move freely. It's a very delicate balance.
Okay, so it's not magic. It's just really clever engineering.
Extremely clever engineering. Finding materials with just the right properties.
And these TCLs, they're part of a bigger structure, right? The patent calls it a tandem photovoltaic device. What does tandem mean here?
Good question. Tandem essentially means stacking multiple solar cells, or thin film junctions, one on top of the other.
Like a multi-layer.
Exactly. A multi-layer device. Instead of just one layer trying to absorb all the sunlight, you have several layers, and each layer is optimized to capture a different part of the light spectrum.
Ah, I see. So one layer might grab the blue light, another the red, maybe infrared.
Precisely. You might have a top cell optimized for higher energy photons, like blues and UV, and then layers underneath designed to catch the lower energy greens, reds, and even infrared light that passes through the top layers.
So you're wasting less sunlight.
You're wasting much less sunlight. By capturing a broader range of the spectrum, this multi-junction approach aims to significantly boost the overall efficiency compared to a single-junction cell. More bang for your buck, photonically speaking.
Okay, let's visualize this. The patent has diagrams. Figures 2 and 5 are helpful. If we slice one of these cells open, we see the stack. It's like a high-tech sandwich, or maybe a lasagna, as the outline suggested.
Yeah, a solar lasagna works. Each layer has a very specific job. Let's start at the bottom.
Okay.
You've got the substrate. That's your base. The foundation could be glass if you want the whole thing transparent, or maybe something else if not. It provides the structure, usually pretty thin, maybe 100 to 2,000 micrometers.
Got it. The plate for the lasagna. What's next?
On top of that, you usually have a back contact layer. This is the first electrical connection point. It needs to conduct electricity well. Materials like molybdenum or tin oxide are common here.
So that's where the electricity starts its journey out of the cell.
Right. Then comes the real powerhouse,
Mm-hmm.
the absorber layer.
Mm-hmm.
In a tandem cell, you'd have multiple of these. This is where sunlight gets absorbed and turns into electrical charge carriers, electrons, and holes.
And First Solar is known for using cadmium telluride, or CDTT, right? Is that used here?
Yes, CDT is heavily mentioned as a key semiconductor, especially for one of the main absorber layers. It's incredibly efficient at absorbing light across a good portion of the spectrum. We're talking super thin layers here, maybe half a micron to 2 microns thick. Other materials are mentioned too, like cadmium selenide or CIGS, depending on the specific junction's purpose.
Okay, so light comes in, hits the absorber, creates charge. What happens next? I see a buffer layer mentioned. What's that buffering?
Good catch. The buffer layer is like a protective intermediary. It sits between the absorber and the next layer, often the transparent conducting layer.
Why?
Well, these interfaces between different materials can be tricky. The buffer layer protects the sensitive absorber layer from potential chemical reactions or damage during the manufacturing of the next layer. It also helps ensure a good electrical contact without hurting the absorber. Think of it as a primer or a sealant. Materials like tin oxide or zinc magnesium oxide often get used here. Very thin, maybe 100 to 600 angstroms.
Right, protecting the vital layers. And then we get to our star, the transparent conducting layer, or TCL.
Exactly. This is the layer that has to do double duty. Let light through to the layers below, or allow light out from layers above, depending on configuration, and conduct the electricity generated.
And the materials, again, were things like ITO?
ITO, yes, or cadmium stannate, zinc oxide, tin oxide, various doped metal oxides. This specific choice depends on balancing the transparency needed with the conductivity required. It's typically quite thin, too, maybe 100 to 600 angstroms again.
It's amazing how thin these functional layers are. Now, I also see mention of a high conductivity layer sometimes near the TCL. Is that just more conductivity?
Pretty much. It's like adding an express lane for the electrons.
Yeah.
Often a doped semiconductor layer, it just provides an extra boost to get the current flowing efficiently out towards the contacts, maybe 300, 500 angstroms thick.
And you mentioned interfaces being tricky. Is there anything else to keep these layers from messing with each other over time?
Yes, definitely. For long-term reliability, you often need a diffusion barrier layer. Atoms from one layer can slowly migrate into another, especially under heat or electrical stress, and that can degrade performance.
Ah, so this barrier stops that migration.
Exactly. It acts like a wall, preventing unwanted mixing between critical layers, like maybe keeping the back contact material from migrating into the semiconductor layers. Amorphous cadmium stannate is mentioned as one possibility. It's crucial for stability.
Makes sense. And finally, is there like a top coat, a capping layer?
Often, yes. A final protective layer on the very top. It can be transparent, and its main job is to shield the whole device stack from the environment. Moisture, oxygen, scratches. Just adds to the overall robustness.
Wow. Okay, so that's one incredibly complex layered cell. But one cell isn't going to power much. How do they make this useful, like for a whole window?
Right, you need to connect many of these tiny cells together. That's called serial interconnection. The patent shows this too. They essentially pattern the layers on the substrate so that the positive side of one cell connects directly to the negative side of the next cell, all on the same piece of glass or substrate.
Just like putting batteries end to end in a flashlight?
Exactly the same principle. By connecting them in series, you add up the voltage from each individual cell to get a much higher, more useful voltage across the entire module or panel. It's how you scale up from a single tiny device to something that can cover a significant area and generate meaningful power.
So we've gone deep into the layers, the materials, the stacking. Let's pull back up. What does all this advanced engineering actually mean for, us, for you listening? Why is this transparent tandem approach so important?
Well, the implications are potentially huge. It's about making solar power generation almost invisible, integrated seamlessly.
So instead of needing a field full of panels or covering your whole roof,
You could have skyscraper windows that look normal but are generating power, car roofs, building facades, maybe even greenhouses that generate electricity while still letting the right light through for plants. It dramatically expands where solar energy can be harvested.
that sounds incredibly versatile. So the big advantages are.
Increased efficiency, first off. Capturing more of the light spectrum with that tandem approach means more power from the same area. Then there's the versatility we just talked about, putting solar in places it couldn't go before because it's transparent.
Right. Energy without blocking the view.
Then durability and reliability. Those buffer layers, diffusion barriers, capping layers, they're all designed to make these devices last longer, even with these complex structures. And, potentially, manufacturing efficiency. Thin film techniques can sometimes lend themselves to simpler, large-scale roll-to-roll production, although these complex stacks add challenges too.
It really paints a picture of solar energy becoming much more woven into the fabric of our buildings and technology, not just something bolted on afterwards.
That's the key takeaway, I think. This deep dive shows solar isn't a solved problem. It's constantly evolving. Material science, clever device design. It's all pushing towards making solar power more effective, more adaptable, and yes, potentially even invisible.
So this patent really gives us a glimpse into a future where the surfaces all around us could be quietly generating power.
It certainly points in that direction.
Uh-huh.
The line between just a building material and an energy-generating component gets really blurry. It makes you wonder, doesn't it?
Yeah.
What other surfaces could become power sources if the technology keeps advancing like this?
Yeah. What possibilities open up when energy generation doesn't have to look like energy generation? A fascinating thought. And that wraps up our deep dive for today, exploring the intricate world of transparent solar cells thanks to this glimpse into First Solar's innovation pipeline. It really shows how examining these specific documents can reveal so much about where technology is heading. Thanks for joining us on this exploration.